Sorry.
So, let's start an example from which we'll work some other definitions. But let us say that the polarization of our material inside of a sphere is just a constant. So what we're saying, what I'm taking as my example, is the situation where I've got a dielectric sphere that is uniformly polarized. Right? Same everywhere inside of this material, inside the sphere. And because the polarization is uniform, well, I wrote it, constant, up there, then that means, well, that's good, that the divergence is 0. And I can work out what the charge density on the surface is. The bound charge density. Remember, I erased it, but I defined it as P dot, and now in this case it's R hat because there's my sphere. I'll define my directions like so. Okay. P dot R hat would give me my surface density, and that's just capital P0 cos theta. I have no bulk density. I have only surface density. You might realize why I wrote over there that when you see something that looks like that, maybe when the charge density looks like that, maybe it's going to look like, well, not maybe, it is going to look like a dipole outside of that region. So we recognize that from our homework and all the prior examples. So then, as you did in your homework, you actually satisfied the boundary conditions. And you found out what the relationship between the internal field and the charge density at the surface was. And then from that, the potential. So I'm just going to write that down because you did it for homework. The potential inside is equal to 4 pi P0 over 3 R cos theta. And the potential outside is 4 pi P0 over 3 R cubed over R squared cos theta. And from this, the electric field on the inside, right? So this was all, this is polarization due to the atom, so we've got this sort of some measure. We defined what the polarization of the material was using the equations that I erased over here, right? But now, given that polarization, we can ask, what's the electric field we would measure if we actually measured the field inside the material? And the electric field is minus the gradient of the potential is minus 4 pi over 3 P. So if you actually went inside the material and attempted to measure the electric field, that's what you would measure, right? And maybe one more connection here is that the dipole moment is, when we look at how we defined the potential from a dipole over there, it's all of these terms. So what I'm going to write is that the dipole moment of that polarized sphere is equal to, so this is not a capital P here now, this is the moment of that thing, is 4 pi capital P0 over 3 R cubed. So I take an object, I polarize it uniformly. And the result is that the potential, first of all, the field on the inside is constant. And the potential outside looks like a potential of a dipole with that dipole moment. Just looking at what definitions I need to give you. I have stuff in the notes that you don't really need to go through. Yeah. All right. So I've got all my charges that arise from polarization that I'll call bound charge, and any charge that's due to free charge. And in general, what do I erase? I'll go over here. I can just write the total charge density in a problem. This will include surface charge. It's all the charge, all right? Bound, not bound, free. Well, actually, not bound and free are the same. But bound and free, so I write rho bound plus rho free. But this can include surface charges. Okay, so it's all the charge, all right? And Gauss's law says this, that the divergence of the electric field is 4 pi all the charge. Rho, right, as rho free plus rho bound. But I know what rho free looks like. It, yeah, I could rewrite this as, I lost a minus sign. No, I didn't. I'm okay. Is 4 pi rho free plus 4 pi rho bound, but rho bound is the divergence of the polarization of the material. And that's where a minus sign comes in. And so, divergence of the electric field plus 4 pi times that polarization that we defined for the material is 4 pi rho free. Now, the free charge, actually that's the stuff that we can move out of a battery onto a plate. That's the actual stuff that's moving around wires, is the free charge, okay? So this is the stuff that's used to charge up capacitors, for example. It's the free charge that we see moving in and moving out, right? If there's a dielectric in the capacitor, then the bound charge moves around, but it never leaves the dielectric of the capacitor itself, right? So I've got a relationship here, which now looks more complicated than what I had before. Remember what we told you before was that the divergence of the electric field in the absence of material is equal to 4 pi times the charge density. We just corrected it to include the free charge, to separate it out, the free charge and the bound charge when there's a material there. Okay. Then we said, okay, we can rewrite the bound charge in terms of divergences, and we end up with the polarization of the material, right? And now I have a modified Gauss's law. And I think that I just lost a dot there.
Yeah.
Yeah. A modified Maxwell's equation, Gauss's law, right? That is now related only to the free charge. Now we're going to rename something, and you want me to hold on for a minute, or you have a question?
Just a quick question. Am I mixing up my p's, or is del dot p 0? Because we said p is constant, or are those different?
Because the polarization is a constant.
Yeah.
It is.
Then wouldn't that just be 4
It
pi?
doesn't have to be constant.
This is This is more general?
This is more general.
Okay, so this is not
I
applying.
finished that example, and I said, we have now, okay, we polarized that. There's an example of how you get the surface charge and what you do with it. And I probably should have erased all of that and then said, now let's talk about these ideas of bound and free charge.
Okay.
In general.
Now that makes sense.
Okay, good. And so now we're going to rename something. We're going to create a new thing that we'll call the displacement field. And we'll define it as E plus 4 pi P. And now, divergence of that D field is equal to 4 pi times the free charge in the problem. So this thing, the corrected electric field, right? The electric field is still the electric field as far as the work that you do to get from one place to another and all of that. It's still there, right? So I shouldn't call it the corrected electric field. The D field, the displacement field, obeys Gauss's law with only the free charge under consideration. We don't have to worry about whether there's a dielectric in there or not. But we do have to ask, are we dealing with free charge or are we dealing with bound charge? And that then leads to a set of fundamental relationships and boundary conditions that we can apply then to any problem, whether there are dielectrics, free charge, bound charge, any geometry, any structure of dielectric, any density of dielectric, whatever, we can solve any problem. But it might involve a lot of hard arithmetic, but in principle we've got it solved. Yeah. I'm going to write one more definition here, which is that this field, the displacement field that's due only to the free charge, okay, is equal to this constant we call epsilon here times the electric field of the total charge in the problem. So the real electric field is this one here. When we do work moving a charge from one place to another point, we use this field. All right? This is an idea. The D field is an idea. Right? But it then is equal to this epsilon times the electric field. Epsilon in this context is called the dielectric constant or the dielectric function, right? And in physics 2, we might have written something like this, where we say that the dielectric constant is equal to kappa times epsilon naught. So this was physics 2. All right? And that's the multiplier by which epsilon is greater than the dielectric constant of, dielectric permittivity of free space. Our epsilon here, because epsilon naught is 1, is the same as the kappa. So when you are comparing equations in the two systems and you find kappa, that's what epsilon is for us. And most of the textbooks write it as kappa, epsilon naught. Yes?
Wasn't it 4 pi epsilon naught we said for 1? So,
Yeah.
shouldn't that be shouldn't there be a 4 pi in there?
No.
Why not?
Don't know.
Because we're in CGS units in the 4 pi.
I can say for
There
sure.
is a 4 pi.
All right, I'll give you a bunch of quick definitions and see whether that just sort of blows you away enough so that you stop asking questions. All right. We're going to define the linear susceptibility, I wasn't going to do this, as some constant, which we call chi, times the electric field. So the polarization of the material, polarization density of the material, is related to some number times the electric field. By the way, that's not true. Right? Physically, it's not true. What I really mean, first of all, is that this is a tensor, and then I have more terms here, and I can't remember how I multiply them together, so I'll write it like that. Ugh, I can't remember. Here's higher order in E. So I'll just write E squared, but I've done the arithmetic completely wrong here. Basically, when you attempt to you have an atom, and you apply an electric field, and it begins to polarize. Initially, as you polarize it, the degree of polarization, the dipole moment, is linear in the electric field that you apply. But when you pull hard enough, when you put enough electric field on there, then you start actually really distorting the wave functions in a way that the atom doesn't like, and it starts costing a lot more energy to pull the positive and negative charges apart. And then after a little bit, it becomes much easier, because now they've moved too far apart. Right? So the dielectric function, or what's called the permeability, is dependent upon the magnitude of the electric field. What we're doing here is assuming linearity, linear susceptibility. And what we're doing here in this course is assuming that that's not a tensor, that that's isotropic. Well, it is a tensor, but we're assuming that it's a diagonal tensor.
So what you're saying basically is that's an approximation.
Yes. Okay. But wait, there's more.
How good an
I thought that I
approximation is that?
confused you enough. Right? So this is what we did, right? There's the 4 pi is there, all right? So we're going to write that as 1 plus, well, not just going to write it, by that definition. All right? Now we'll define epsilon as 1 plus 4 pi pi. All right, so I buried the 4 pi.
Isn't that 1 plus 4 pi psi E?
Oh,
Chi.
but he was right about the E. Okay? No.
Seems legit.
I hit it. That's the bottom line. So that's okay. And for those who are interested, there's a whole page of notes on this.
You could look back on the Schroeder's notes on this in optics.
Yes.
How good an approximation is it assuming linearity with chi?
Very good. Up to...
When the E field's low.
Okay, so for... Yes. But the question is, what's a low E field? It's a good approximation up to about... Unfortunately, my problem is I only know these numbers in MKS units, right? Around 10 to the 5th volts per centimeter. So 10 to the 7th volts per meter. You're okay up to. All right? Most of your sources that you've got are, maximum. Actually, we won't give you anything more than 12 volts in the laboratory. For safety purposes, but let's say you've got 100 volts, and that means that you've got to put those two plates 10 microns apart. So you could do it.
It's just really
100
hard.
volts across a piece. No, a piece of paper is 100 microns thick. So 1,000 volts across a piece of paper. Right, and then actually, you know what happens then? It goes. and that's when it's just gone nonlinear.
It arcs.
Now, one way to get really high electric fields where you don't actually fully break down the material is by having very intense light beams. So those extra terms become much more important in optics, and it's possible to have to actually go out to the fifth order, where the fifth order is an observable thing. But in order to do that, you have to take, let's say if you had a CW beam, a constant laser beam, you would have to focus it down to about, you'd have to have about 100 watts in your laser beam, which is really big, all right? Focused down to around a micron diameter, and then you'd begin to see the nonlinear effects.
Wow.
Okay?
Also, I need to switch over the media.
All right.